In this section, we're going to talk about the Newton's method, or also known as Newton-Raphson method for root finding. In previous sections, we learned about bisection and secant methods. They are very similar, and actually bisection can be seen as a special case of secant method. Both of them start with a range, and they suggest a third point in that range, and then continue with one of these ranges, A to C or C to B. In bisection method, the suggested point is the midpoint of the range, but in secant method, we approximate the function with a line which connects these 2 points to each other, and the zero crossing point will be our next guess of the solution, and then we continue with A to C or C to B. Both of these methods, secant method and bisection, has guarantees about convergence. And in Newton method, we don't work with ranges or intervals, and so we don't have any guarantees about convergence or finding a root. However, if this method converges, it will be very fast. So let's see how Newton's method works. Let's assume that we're going to find the roots of this equation, and also this is the plot of the function fx on the plane, and we have the plot of f of x as this, y equals to f of x, and we start with a point known as initial or starting point, and then we will improve this solution. Here we don't work with intervals or ranges, so assume that we have this point or this value of x as a starting point, and then we're going to find a better suggestion. To have the next suggestion, we're going to approximate this function with a line, but this time we have a single point, not 2 points, similar to secant method. We have a single point, so the line must pass through this point, and it must have same slope as the derivative of function at this point. We match the 0th order derivative and first order derivative of line with the function, and we have the tangent line of the function here, and this tangent line has 0th order and first order derivatives equal to the original function. What's the 0th order derivative? That's the function value, because it passes through this point. So at this point, if we find the value of y, then we will get f of x0. And if we calculate the derivative of this line, and that's also known as the slope of this line, then it will give us f prime of x0, and that's the value of first derivative of function at this point. And you know that you can express this tangent line by this equation, y equals to x minus x0 times f prime of x0 plus f of x0, and that's the equation of this tangent line. And to find the next suggestion, we must find the point where this tangent line crosses 0, and that's our next suggestion, for example x1, and then we continue this procedure again and again, and possibly or potentially we will converge to a root. And there are no guarantees to have convergence in Newton's method, but if it is convergent, then it will be very fast. Let's see what's the root of this equation. We have the tangent line described by this, y equals to x minus x0 times f prime x0 plus f x0. Let's find where this line crosses 0. Then if we solve for x and name the root equals to x1, then it can be expressed as this: x1 equals to x0 minus f of x0 divided by f prime of x0. And next, we use the same equation to calculate x2, which is equal to x1 minus f of x1 divided by f prime of x1. And we can convert this equation to a general equation, a recurrence relation in this form, and that's xn equals to xn plus 1 equals to xn, the previous guess, minus f of xn divided by f prime xn. And that's the recursive equation of Newton's method for finding new guesses based on the old one. And that's it. That's the core equation of Newton's method. And you see, we have some limitations here. For example, if f prime is very close to 0 or 0, then this will break and cannot be evaluated and cannot be gone forward. And we have some limitations, but if Newton's method is going to be convergent, then it will be very, very fast and efficient. And actually, this can be used as a method for perform optimization too. And some optimization techniques derived from this equation solving technique. Okay, I'm going to implement this method to solve previously solved equations. One of them is this, and the other is this. First, let's use Newton's method to solve this equation, and I'm going to start with Python to implement the Newton's method. Okay, let's start with the Python implementation of Newton's method. I'm going to create a file named newton.py here, and let's import math module here. I'm going to define the function Newton, which accepts a function, a starting point x0, a level of tolerance, which is default value this, and we have the maximum number of iterations here. 100 will be enough as the default, I think. Okay, let's set the current solution equal to x0, and let's evaluate this using f of x. And if absolute value of this fx is less than tolerance, then we already provided a solution which is acceptable. So we can return x as the result. In case we want to enter the iteration loop of Newton method, we're here and we have a for loop for some dummy variable in range, max it, and we're going to calculate the next solution we have. Let's define x new, the next solution we have, as x minus f of x divided by f prime of x. And we don't have the value of f prime of x in this formula. It is the value of first derivative of function at the point x here, and we must calculate this. So we must have a function, for example fp here, or we can calculate this using some numerical differentiation method. I'm going to use that. So I'm going to define a function which calculates the derivative of a function at a given point with some delta x, difference of x, which is default value is 1e negative 6. It's a very small value. But let's have a look at the definition of function derivative here. We know that the derivative of a function at a specific point is given but by this limit of this fraction f of x plus delta x minus f of x divided by delta x, where delta x goes to 0. And here this point approaches x from right hand side. Similarly, we can have another definition here, limit of f of x minus f of x minus delta x divided by delta x, where delta x goes to 0. And this approaches from left-hand side, assuming that delta x is a positive number. And if we combine both of them, we can have a central definition here, and that's given by this: f prime of x is the limit of this fraction f of x plus delta x minus f of x minus delta x divided by 2 times delta x, where delta x tends to 0. And we have this central definition of function derivative here, and we're going to use this. Just calculate the value of a function at x plus some small value and x minus some small value, then divide the difference by 2 times difference of x. So I'm going to calculate this. Difference of f is f of x plus dx minus f of x minus dx, and we're going to return df divided by 2 times dx, and that's it. We calculated the derivative of function at a given point numerically. We approximated this. So we can calculate fpx as derivative of f at this point x, and using the default value of dx, and that will be fine. Here, actually, we don't need a new symbol, x new. We just replace this with x. And here, we evaluate fx as f of x. And finally, if absolute value of fx is less than tolerance, then we can go outside of the loop. And here, outside of the loop, we can return x. Also, we must take care of fpx here, and if fpx, actually absolute value of fpx, is very, very close to 0, for example, if it is less than tolerance, then we can go outside of the loop, or we can print some errors. And that's it. We have the conditions on the derivative of function. We have new suggestion, new guess point, and we are checking for f of x. And you know that this can also be merged with this, and they are identical. And we can move this to the beginning of loop, and finally remove this from here to make the code shorter. And that's it. That's the Newton-Raphson method with derivative function calculated numerically here. And now we can define a function which is a lambda function of x squared minus x minus 1. And I'm going to start from, for example, 2 as the starting point, and I'm going to find the solution of this equation, Newton, using the Newton method, calling func, and starting from x0, and tolerance equal to 1e negative 10, and max it equal to 100. I'm writing these to make possible to change them. And also, let's print out the solutions here. Solution is given by this: x equals to this, and f of x equals to this dot format, and we have x here and func of x here, and that's it. Let's run the code and see what's the result. You see we have the result here. It's the result we expected to get, and it's the function value here. And also, if we want, we can use the same code for func2, x squared minus minus math.exp minus x minus 1, and start from 2, and we have x0 here, same tolerance value. Let's change this to func2 and have the results of the second equation. Oh, sorry, we must change this also to func2, and let's run this. And this is the solution for the second equation, and this is the first equation, and that's fine. And we found this solution. Okay, you see that we implemented the Newton method in Python, which solves the equations, and the results are similar to those we have by using bisection and secant method. And I'm going to implement the Newton's method in MATLAB as well. Okay, let's implement the Newton's method in MATLAB, the Newton-Raphson method. I'm going to start a new function which returns x as the root of function, and Newton-Raphson, I'm going to use this name here, and it accepts a function and a starting point, a level of tolerance, and max it. And first we evaluate the solution x equals to x0 and fx equals to function value at this point, and if absolute value of fx is less than tolerance, then we must return, because we use the same variable name here for this, and we can return, and x is already set, and we have to include semicolons here. And also I'm going to create a for loop for it equal to 1 up to max it. And let's define the next point suggested by Newton's method. X new equals to x minus f of x divided by f prime x. And similar to Python and using this limit definition of derivative, I'm going to create a function which evaluates the function derivative at a given point. So I'm going to add another function in this script, in this file, and it returns, for example, df divided by dx, and derivative, or I can use derivative of f in a given point and with some value for dx. And I'm going to calculate df, f of x plus dx minus f of x minus dx, and df dx equals to df divided by 2 times dx. And that's it. That's the derivative of function f at a given point x. And let's save this. And also fpx equals to derivative of this function at this point using this dx, and let's define dx equal to 1e negative 6. It will be fine. And this fpx is very small because we are going to divide by this. It cannot be 0. Then we check if absolute value of fpx is very small, then we go outside of the for loop. And here we have the name x new. I'm going to use the same name for the variable, and I'm going to evaluate this f of x equals to f of x, and we check if absolute value of f of x is less than tolerance, then we found a solution, a potential solution for the equation, and then we can go out, we can break the for loop. And similar to Python code we can merge this if with this if, they are identical, and I'm going to remove this and paste this at the beginning of for loop and remove this as well, because if we enter the for loop, then we have the same if here, and after this, if we have evaluated fx and we return back here, and if the value of f of x is less than tolerance, then we can go outside of the for loop. And here, because we assigned x, there is no need to any statements in the form of return or anything similar. Okay, that's it. We created the Newton-Raphson method here, and we have the derivative here, and I'm going to use this. But let's copy, for example, these two functions, and I'm going to rename them to Newton1 and also Newton 2. And okay, let's open these. This is the first equation we have here. We have a x0 as 2, and I'm going to use Newton Raphson here and pass func, and instead of a and b we have x0 here with using this tolerance and max it. We define the function as a function handle, we define a starting point here, we define the tolerance value here and the maximum number of iterations, and we call Newton Raphson function using these parameters, and this is the value of x. So we have this, let's call Newton 1, and that's the solution we have, and this is the function value here. You can calculate the func of x here, and that's 0, very close to, for example, 1 plus sqrt 5 divided by 2. That's the value of exact solution, and if you compare this to x, you have 0 error here, and it's very accurate. Here we can copy this into the next function and change this to have another equation, a nonlinear equation. Start from 2, and this tolerance, this max it, same structure. I'm going to run this as well. So let's clear the screen, and Newton 2, and we have this solution, and the function value here is very close to 0. So we implemented Newton Raphson method from scratch in Python and MATLAB, and these are very simple methods: bisection, secant method, Newton method, but they are very useful, and knowing how to implement them using 2 programming languages enables you to implement them in what language you want, and knowing about the theory behind them enables you to use them in your applications and even develop your methods or improve these methods to have better performances. Okay, that's it. We've finished with this video tutorial on root finding methods from theory to implementation. I hope this course was helpful for you, and I'm waiting to have your comments, suggestions, questions, or anything else on yarpus.com, YouTube, Udemy, or wherever you're watching this video tutorial. Thank you for watching and wish you the best.